Here we apply our hydrodynamics equations, the continuity equation and the Bernoulli equation, to a standard example scenario called a Venturi tube. So we've got a tube full of liquid water, let's say. Here's a horizontal section, and coming off of that are pipes that are open to the air here, these vertical sections. So in blue is our fluid, and in yellow is the surrounding atmosphere at a pressure of 1 atmosphere. So we've got vertical distance measured in meters and horizontal distance here. Suppose our pipe is open on the left and on the right so that the fluid could come in this way and go out that way. But at the moment, the pipe is full and the water is not moving. We are in a state of hydrostatic equilibrium. So we've got water filling up these two vertical sections of pipe, which again are open to the air up here. And they are at the same vertical height, of course, if we're in hydrostatic equilibrium. And we've set that to a height of 0 meters here. So you can see -1, 2, 3 meters below this reference level. To work out the pressure down here at point 1 and point 2, we'll use our hydrostatic equilibrium equation that the difference in pressure in a fluid between two different heights is equal to the density of the fluid times little g times the distance between those two locations. So, for instance, the pressure here at point 1 can be found by comparing point 1 to this point here at the top of the fluid, at the sort of liquid air interface right there. We know that the pressure here at the interface is 1 atmosphere. So we say that the pressure down at point 1 is equal to the atmospheric pressure above the column plus the density of water times little g times the depth of that column. That depth would be 1, 2, 3, 4 meters here. So that'll be 1 atmosphere for the atmospheric pressure up here, and then add to that the density of water, which is about 1,000 kilograms per cubic meter. And we're going to use approximate values here. So for little g, we use about 10 newtons per kilogram, and our depth with 4 meters. We'll need to do some unit conversions here. So these are all in SI units. That's going to come out to 10 to the 4th times 4, so 40,000 newtons per square meter. And a reminder that 1 atmosphere is 101,325 newtons per square meter. That is equivalent to 101,325 pascals. 1 newton per square meter is the same thing as a pascal in the SI system. So it's often called 101.325 kilopascals. But in any case, that number is about 10,000. No, about 100,000. So 1 atmosphere roughly is about 10 to the 5th newtons per square meter. So this value here, which is about 40,000 newtons per square meter, that is about 0.4 atmospheres. So 1 atmosphere plus 0.4 atmospheres is about 1.4 atmospheres. That'll be the pressure down here at point 1. And over here at point 2, since it's at the same level and we are in hydrostatic equilibrium, the fluid is not moving, these two pressures will be equal. So we can say that the pressure at point 2 is equal to the pressure at point 1 before anything moves. But this is supposed to be about hydrodynamics. So now let's picture what occurs if we set this fluid in motion. Suppose the fluid in our pipe here starts moving from left to right. Then we notice that we've got a wide section and a narrow section here. And we know based on the Bernoulli effect that the fluid will be going faster here at point 2 than at point 1. Once it starts flowing to the right, it's going to speed up as it enters the narrow section. And for it to speed up as it enters the narrow section, we know that the pressure here at 2 in the narrow section is going to have to be lower than the pressure here at 1 in the wide section. High pressure, slow moving, switches to low pressure, fast moving once we've got flow. So at that point, once the pressure here at 1 is higher than the pressure at 2, then this fluid here at 1 will be able to support a taller column of water. It can support more weight if the pressure is high here. And if the pressure at 2 is low, if it drops, it won't be able to support a column of water as high. So we expect that when fluid starts flowing through this pipe here from left to right, that the column of water here above point 1 will rise and the column of water here above point 2 will drop. The situation will then look like this once we leave hydrostatic equilibrium and we are instead in a state of steady state flow. Here are three streamlines with a Q, a flow rate coming in at the left, matching the Q, our flow rate going out at the right. Here's gate 1, where these 3 streamlines pass through, and then gate 2, the same 3 streamlines, they're now more bunched together because the fluid is moving faster. It passed through there as well. And we're expecting a higher column of water and then a lower column of water above these 2 points, since now the pressure at 2 is not equal to the pressure at 1, even though they're at the same horizontal level, since there is horizontal flow. But our hydrostatic condition still holds in the vertical direction. It's still true that the difference in pressure between any 2 points vertically, as long as there's no vertical flow, is given by this expression right here. So we'll still find the pressure here at point 1 by comparing point 1 to the top of our column of fluid, where we know since the water is open to the air up here, the pressure here is 1 atmosphere, matching the surrounding air pressure. So the pressure at 1 equals the atmospheric pressure plus rho g times d, where d is the depth of this column, which is now 1, 2, 3, 4, 5, 6 meters deep. Pressure at 1 is the atmospheric pressure, plus that 6 meter deep, plus the term for the 6 meter deep column of water. The pressure over here at 2, we can find from the same argument. Pressure at 2 is equal to the pressure here at the air-water interface, plus rho gd, where the depth here is 1, 2, 3 meters deep. So I guess we should say rho g d2 versus rho g d1 right there. Okay, so let's find the new pressures at these 2 locations now that the fluid is flowing. Recall that in the hydrostatic case a moment ago, the pressures here at 1 and 2 were both 1.4 atmospheres, since they were 4 meters deep. Now with fluid flowing, we've got a 6 meter column above point 1, so that's going to correspond to 1.6 atmospheres of pressure at point 1, and a 3 meter column above point 2 gives us a 1.3 atmospheres above point 2. So the pressure here is dropped here at 2 once the fluid started flowing from 1.4 to 1.3, and the pressure here at 1 rose once the fluid started flowing from 1.4 up to 1.6. So if we know these 2 pressures, we can now use the continuity and Bernoulli equations to compute what the speeds of the fluid must be passing through gate 1 and gate 2. Our continuity equation says that the flow Q at gate 1 equals the flow Q at gate 2, so A1 V1 equals A2 V2. And if we know the difference in diameter, so suppose the cross-sectional area at gate 1 is twice the cross-sectional area at gate 2. So if this area is double that area, then the speed at 2 will have to be double the speed at 1. We know the fluid speeds up as it goes into the narrower section. That speed will have to be double what it was at 1 if the cross-sectional area is cut in half. So our continuity equation tells us how those speeds are related. We don't know the speeds yet, but we know how they're related now if we know what the areas are. And so we turn to the Bernoulli equation, where we will look at this streamline that flows right down the middle and compare 2 points on that streamline, the points where that streamline passes through gate 1 and the point where that same streamline passes through gate 2. Where it passes through gate 1, we add the pressure at that point, plus the kinetic energy density at that point, plus the gravitational potential energy density at that point, and set that sum of those three terms equal to the same three terms at gate 2. We look for terms that'll simplify by canceling out, and note that those 2 points on the streamline are at the same height. So those 2 terms are identical, so we can subtract them. They'll cancel out. And now let's rearrange to try and solve this for the speed at gate 1. So I'll move our pressure terms over and our kinetic energy density terms to the other side. Then make use of the fact from the continuity equation that we know the speed at 2 is double the speed at 1 based on the change in cross-sectional areas. So we'll place the speed at 2 with twice the speed at 1. Then we're going to square both those terms, so that'll become a 4v1 squared. 4v1 squared minus v1 squared. Once we factor out the 1/2 row, this would give us a 3v1 squared, leading us to here. And now let's finish rearranging this to get a v1 by itself. So I'll multiply both sides by 2/3, divide both sides by row, and then square root both sides to get v1 equals this expression here. And we found those two pressures, P1 and P2, 1.6 and 1.3 atmospheres. Now to do our calculation, we're going to have to convert those atmospheres to pascals. It has to be in SI units. So we'll note that the difference is about 0.3 atmospheres. 1.6 minus 1.3, the difference is 0.3. And that is equivalent to, well, we know that there are about 10 to the 5th pascals in 1 atmosphere. Where pascals is the same thing as newtons per square meter. That's our SI unit. So that'll be 0.3 times 10 to the 5th is what we would put in here. So 2 times 0.3 times 10 to the 5th divided by 3 times 10 to the 3rd and square root gets us the speed at 0.1. So look at that. If we know the heights of these two columns, and we know the widths of the pipes here and here, that's enough information to conclude what the speed of the fluid must be here at gate 1. We now know the speed by using our continuity and Bernoulli equations. We found the speed at gate 1, which means since the speed at gate 2 is double the speed at gate 1, we also know the speed at gate 2. We can solve for both of those speeds. For completeness here, let's do a quick bar graph comparison. At gate 1 and gate 2, at gate 1, we've got, using our 3 terms from the Bernoulli equation, we've got some kinetic energy density, some gravitational potential energy density, and we've got pressure here. And from gate 1 to 2, we know we gained kinetic energy density. Since the speed went up by a factor of 2 and speed gets squared in that formula, our kinetic energy density must go up by a factor of 4. Therefore, at gate 2, we know we have 4 times the kinetic energy density that we had at gate 1. But it's at the same vertical height. So we have the same amount of gravitational potential energy density. And so that gain of 3 units of kinetic energy density, that must have come from the loss of 3 units worth of pressure. And if we count boxes there, we went from 16 boxes worth of pressure at point 1 down to 13 boxes worth of pressure at point 2, matching these values here for the pressure drop going from the wide, slow-moving, high-pressure part to the narrow, fast-moving, low-pressure part. And here's the Bernoulli equation showing conservation of energy in that transition.